right, so we want to build a BLT. What's a BLT? Bacon, lettuce, tomato sandwich, right. So, in terms of ingredients, what do I need?
Bacon.
Just, so, can we be more specific about bacon? Think in terms of quantity. What's that, Trinity?
What was your question?
Can we be more specific about bacon? Like, we need bacon for our sandwich.
Cooked bacon.
Okay, cooked bacon. Let's assume it's cooked.
Juicy.
What about pieces?
Sliced.
How many? 3? 4, 3? What do you want? It's your sandwich.
Three.
I love bacon, so I appreciate 3 million. You don't? Okay. You're gonna make the sandwich in your mind, but you're not gonna eat it. Okay, you don't. I'm not gonna make you eat it, but we're going to assume because it's a BLT, we got to keep our bacon. So let's go with 4 strips of bacon. We're gonna say bacon is B. Okay. I mean, that's the first letter in a BLT. It's bacon. What else do we need?
Some freshly sliced lettuce.
Lettuce. Okay. So I don't know how much. What would you say? Let's call it a leaf of lettuce. 3 leaves. Again, this is all hypothetical, so it is what it is. 3 leaves of lettuce. We'll call that L. Okay. Well, the T part is obviously tomato. How many slices of tomato? 2 slices? Do I hear 3? No tomato at all, Amelia? I don't like tomato on my BLT either, so it's a BL. And my wife loves it. She put like 5 slices on if she could. Is 3 good?
Yeah.
Let's say they're small enough that we could fit 4 nice and even. So we'll do 4 slices of tomato. Okay. Well, that's definitely the BLT part, but obviously we're missing some key ingredients. Let's start with the bread. 2 slices, I'm assuming? Unless we're doing a triple decker, but we'll do just a regular sandwich. 2 slices of bread. So I'm gonna see BA for bacon, and I'm gonna see BR for bread. Maybe you can kind of see where I'm going with this. Anything else you like on your BLT? Who loves a good BLT? You sound like you've had a BLT before. Anything else on it?
Mayo, salt, pepper.
Okay, salt and pepper, that's kind of hard to measure, but mayo?
Yeah.
Okay. Anything else you said? Mayo? Okay. So we'll just say 1, whatever a dollop is. I like that word. We'll say mayo. I don't want to get too carried away, so we'll just leave it at that. Salt and pepper for taste, but yeah, we're not going to worry about that. Okay. So if I put this together into kind of like a chemical equation of sorts, then it would look something like this. So that would be kind of what we're looking at in terms of a recipe, but it also kind of reminds us of a chemical equation. And when I look at a chemical equation now, and when you look at a chemical equation, particularly a balanced chemical equation, One of the things you'll notice is that mathematically, the numbers on the left don't necessarily add up to the numbers on the right. You can see this with any balanced equation that you had on worksheet 3 from, I can't remember when it was, way back last week. And you'll notice that the coefficients don't add up, but they don't have to. It's the atoms that have to add up. So, for example, our 4 slices of bacon, our 3 slices of, 3 slices of lettuce or leaves of lettuce, our 4 slices of tomato, or 2 pieces of bread, and our 1 dollop of mayo are all represented in that one sandwich. So everything on this side balances everything on that side. Yet our product is just one thing, whereas our reactants were 4, 7, 11, 13, 14 things came together to make that one sandwich. So you see what I mean? But more importantly, if I don't follow this recipe, I'm not going to make the same BLT each time. Now I understand, and again, like each one of you might have a unique recipe. Some of you might not have the bacon on it. Some of us might not have the tomato on it. We might add something else, maybe mustard, although that sounds weird. Like I said, maybe you want to have 3 slices of bread and have a triple decker. So maybe that means you're changing, maybe you're doubling up the bacon if you really like bacon. The point is each equation is going to be different, but it still has to balance. Okay? So when I say this as a chef, any recipe that you look at, if you're making a cake, pancakes, I don't care what you're doing, when you look at your ingredient list, it's 4 parts of this, plus 3 parts of that, plus 4 parts of this, plus 2 parts of that, plus 1 part of that gives me my product. Same thing with pancakes. The thing about pancake recipes is that it'll actually tell you how many pancakes that amount of materials will make. It'll probably say like 12 to 14 pancakes. So now you do have a number over here, whereas a cake, you're making 1 cake. So all the ingredients add to 1. So now how does this translate to a chemical equation? Well, as you can imagine, quite literally the same way. One of the most common reactions that we start with is hydrogen gas burned in the presence of oxygen gas. Any idea what that makes? When you burn hydrogen and oxygen? It's one of the cleanest reactions. It's what we're trying to strive for when we talk about clean energy. What product has hydrogen and oxygen in it that might be really clean? And you might be thinking about it if you're thirsty.
H2O.
Simple product of this reaction is water. Usually water vapor, but it could be, some of it will come out as liquid vapor or liquid. And that's what the G's represent. You don't have to worry so much about that. That's just a habit. Now, is this a balanced chemical equation? No. Hydrogens are happy, but the oxygens are not. If I put a 2 here, that gives me 2 oxygens. Now I have 2 oxygens, but now it changes my hydrogens. Mind you, a simple 2 here fixes everything up. And here's a perfect example of where I said you can't treat the coefficients as numbers. In other words, 2 plus 1 does not equal 2. We know that. However, in this recipe, 2 parts hydrogen and 1 part oxygen does equal 2 parts of water. And if you kind of take a look at our Lewis structures, you remember what these look like. So this was, that's hydrogen. Here's oxygen. And now we have 2 hydrogen molecules. So, and over here, really, that's what we're looking at. So visualizing a chemical reaction. So here's my water molecule, 1 oxygen and 2 hydrogens. This is what I originally started with, right? We'll take that away. You can clearly see that things aren't going to balance up visually. So we need to bring in another water molecule, so that gives us our 2 oxygens, and 1, 2, 3, 4, 1, 2, 3, 4 hydrogens. Okay? So, the other way to say this now is this number. And really, there's a 1 here, right? Normally we don't write it in, but I'm going to put it in there for now. If I was going to speak this reaction, I would say 2 moles of hydrogen reacts with 1 mole of oxygen to produce 2 moles of water. That's what I want you to think about, and that's what I want you to say in your head when you look at a balanced chemical reaction. Notice that we brought the term moles in now. The other thing that you can think about is, well, what's the molar mass of hydrogen? H2 is the formula for hydrogen. So if we look on the periodic table, 2 hydrogens is 1 plus 1, that's 2, times 2. So we have 4.0 grams per mole. Oxygen, O2, so twice oxygen. So oxygen is 16.0, so that's 32.0 grams per mole. Water is 16 plus 1 plus 1, so 18, but there's 2 of them. So I have 36. Sorry, that's 36 grams, not per mole, my apologies. So I have 36 grams of water. And you'll notice that 4 plus 32 equals 36. So that's that whole law of conservation of matter part. Okay. Any questions about that? I'm going to try and save this reaction here, just so I don't have to write it down. Okay, so here's where that recipe part comes in. Well, dealing with moles is great, but again, if I want to make a certain amount of water, then I need to work in grams. We know that 1 mole of water is about 18 grams. That's 18 milliliters. So let's say that we wanted to make a liter of water. So a liter of water is 1,000 grams, because 1,000 milliliters is 1,000 grams. So let's say that we wanted to make 1,000 grams of water. How much product would we need? So we'll use X and Y. So we want 1,000 grams, but we don't know how much reactant we need to start with. So in order to figure that out, we kind of work with what we have. So just as we did previously we start with 1,000 grams of water. You'll remember earlier that I talked about how everything has to go through moles. So we have to talk about moles in order to convert from water into oxygen or hydrogen. So before we get to that, let's just talk about our mole ratio one more time. So this tells me that I need 2 moles of hydrogen to make 2 moles of water. You okay with that? How many moles of hydrogen would I need to make 4 moles of water? So if I want to double this, what would I have to do to the hydrogen? Yeah, okay. Don't think harder, or don't make it harder than it needs to be. So if I want to double the amount of product, I need to double the ingredients. Think about, again, your pancakes. Let's say you're cooking for 6 of you. So maybe 12 to 14 pancakes isn't enough. So now you want to double that recipe. So you would double all the ingredients to make twice as many products. Likewise, if I wanted to double, so if I wanted 4 moles of water, I would also need 2 moles of oxygen. What if I wanted 10 moles of water? And I'm trying to stick to whole numbers right now. So if I wanted 10 moles of water, how many times more is this? Or how many times more is that? 5. So if I want to make 5 times more water, I need 5 times more ingredients. So I would need 10 moles of hydrogen and 5 moles of oxygen. So as long as you follow the ratio, and that's what the mole ratio means, as long as you follow the ratio, you're going to make, or you're going to be okay. So if I'm working in moles, in fact, we'll come back to this in a second. What if I wanted, just going to throw out a crazy number. What if I wanted 13.5 moles of water? Can you divide that by 2 now? Not evenly, right? Not evenly. So if I want to know how much of each reactant, well, I can use the mole ratio. And the mole ratio always comes from the balanced equation. So the mole ratio is the coefficients. 13.5 moles of water. Well, I know that the ratio tells me that 2 moles of water requires 2 moles of hydrogen. So now that's kind of easy to see, because I can see that this is a 2 to 2 ratio. Right? Because if you think about water, so hydrogen to water is a 2 to 2 ratio. Oxygen to water would be a 1 to 2 ratio. That's kind of what I want you to think about. Think in terms of ratios. You've done that in the past in math. So moles of water cancels. The 2's cancel. So 13.5 moles of hydrogen are required to make 13.5 moles of water. What if I wanted to find oxygen? Same process. This time it's not a 1-to-1 ratio or a 2 to 2 ratio. It is a 1 mole of oxygen to 2 mole water ratio. In other words, I only need half. It's 13.5 divided by 2. 6.75 moles of oxygen. Which again makes sense, because I need only half as much oxygen as water in terms of moles. Remember, this is going to be recorded too, or I am recording this too, so you can come back and watch it. So moles, hopefully moles are starting to make sense. The problem comes back to the fact, though, that I can't use my balance to weigh moles. So my electronic balance still requires me to do math, or to do mass. So let's go back to the original problem. I want 1,000 grams of water. And I want to know how much hydrogen gas I need to supply, or how much hydrogen gas I need to burn in order to make 1,000 grams of water. Let's say I have enough oxygen, I have plenty of oxygen, but I want to find out exactly how much hydrogen I'm going to need. This is a 3-step process, or a 3 conversion process, but I'm going to say 3 steps because I'm going mass A to mass B. And I'm going to show you the mole map in a second here. But let's say that this is what I'm doing. In order to convert from water to hydrogen, I have to go through moles. And the first and the third conversions represent those conversions between grams and moles. But the first one is water. So remember, I want to get rid of grams of water, and I want 1 mole. Where have I seen that before? How do I find the mass of 1 mole of water? We did some of this on Friday and we reviewed it this morning. How do I find the mass of 1 mole of water? What do we call that? Remember we said it's molar mass. So what is the molar mass of water? 2 hydrogens and 1 oxygen. Not the number of atoms, the mass, right? So if you look up oxygen and hydrogen from your periodic table, what's the mass of oxygen?
2.
The mass. 16. What's the mass of hydrogen? 1. And we got 2 of them. So 1 plus 1 plus 16 is 18 grams. Grams of water cancels. Now I have moles of water. This middle conversion is where we use the mole ratio. So the mole ratio, remember, comes from up here. That's why we always have to start with a balanced chemical equation. And I want grams of hydrogen. So I want the ratio between water and hydrogen, which is a 2-to-2 ratio. And since I have moles of water here, I want moles of water on the bottom. So 2 moles of water. And on the top is what I want, 2 moles of hydrogen. Now moles of water is gone. And I have moles of hydrogen. But remember, I don't want moles, I want grams. So what I want has to be on the top. This is the molar mass of hydrogen. Hydrogen is 1 gram per atom, and I've got a molecule of 2. So this is going to be 2.0 grams of hydrogen in every 1 mole of hydrogen. That cancels. I can cancel some other things if I just want to do some mental math or help myself out a little bit. I can cancel those 2's out because they're the same. I could even do this. I could cancel out the 2 and the 18 and have 9. But again, I'm going to leave that up to you. for the most part, it's just easier to just go ahead and plunk everything in your calculator. So we've got 1,000 times 2, which is 2,000, divided by 18, means that we need 111, that's a lot of ones, 111.1 grams of hydrogen. Have you ever seen therefore before? 3 dots, that means therefore. So therefore, we need 111.1 grams of hydrogen to make 1,000 grams of water. Now, this is something that I can understand. This is something that I can measure out. Assuming we could measure out hydrogen on a balance. Hydrogen's a gas, so it's a little bit trickier. But there are ways around that. Okay, so we're going to practice this a little bit more, obviously. Although in about 10 minutes, we're going to have a nutrition break. But I want to show you I'm just going to pause this. Actually, no, I'm going to stop it.